Hello friends, in this lecture we are going to discuss about chemistry of pyrrole, which is a 5-member heterocycle with one heteroatom, that is nitrogen. So this is a structure of pyrrole, which is simple 5-member heterocycle ring containing nitrogen as a heteroatom. In general, pyrrole is an important pi-accessive aromatic heterocycle. Okay, so it is an pi-accessive aromatic heterocycle because this ring system is incorporated as a basic structural unit in porphyrins, porphine, heme and chlorine, that is chlorophyll and corins, vitamin B12. And pyrrole was isolated in pure form from bone oil in 1857 and its structure was established in 1870. Although the characteristics behavior of pyrrole of imparting red color to the pine wood, moistened with an acid, lead to its discovery in 1834 as a substance present in bone oil and coal tar. So very important test for pyrrole is it gives or it imparts red color to the pine wood lead to its first discovery. Okay, so it was discovered in 1834 and its structure was established in 1870. Now we are going to see the chemistry of pyrrole. Pyrrole has planar pentagonal structure with 4 carbon atoms and nitrogen atoms, which is sp2 hybridized. So sp2 hybridization is present in pyrrole. So its ring atoms forms 2 sp2 sigma bonds to its neighboring ring atom and 1 sp2s sigma bond to a hydrogen atom. The remaining unhybridized p orbital, one on each ring atom with 1 electron on each carbon at 2 electron on nitrogen, are perpendicular to the plane of sigma bonds and overlap to form pi molecular system with 3 bonding orbitals. So this is an overall chemistry of pyrrole. Okay, contains 6 pi electron, 1 pi electron on each carbon atom and 2 pi electrons on nitrogen. So total 6 pi electrons are present. That's why this pyrrole ring is known as a pi-accessive heterocycle. The 6 pi electrons form an aromatic sextet, which is responsible for the aromaticity and renders stability to the pyrrole ring. So the 6 pi electron which we have carbon and 2 on nitrogen, so total 6 pi electrons are very important. Okay, because it forms an aromatic sextet which is responsible for aromaticity. So it gives aromaticity to the ring structure as well as it renders stability to the pyrrole ring. So this is an overall orbital structure of pyrrole. So numbering of pyrrole starts with nitrogen atom. So this is in first, second, third, fourth and fifth positions of pyrrole. If we are going to see in the form of alpha and beta positions, then these are alpha and alpha dash and beta dash. That second and fifth position is alpha and alpha dash. Third one is beta and fourth one is beta dash. So these are the very important C alpha N and C beta to C beta bonds are shorter than the normal single bonds, whereas C alpha to C beta bonds are longer than the normal double bonds. So these are the bond lengths for pyrrole. The molecular dimensions of pyrrole reflect cyclic delocalization with the involvement of lone pair of electrons on the nitrogen. Now we are going to see the resonating structures of pyrrole. Pyrrole is considered to be the resonance hybrid of the resonating structure 1 to 4, that is 1, 2, 3, 4, 5. Okay, which with electron-rich carbons, which lead to its classification as an pi-accessive aromatic heterocycles. So this is the structure of pyrrole. This is the first resonating structure, and this one is second resonating, third, fourth, and final is an structure of pyrrole. So these four resonating structures are very important. So resonating structures in pyrrole is due to the presence of this lone pair on nitrogen, which is very important to show the different resonating structure. Due to the delocalization of this lone pair, pyrrole shows different resonating structure. So initially there is shifting of this lone pair to its nearest carbon atom. Due to that, the double bond formed between carbon and nitrogen, and this double bond shifts to its nearing carbon atom. That's why there is a minus charge on this carbon atom at third position. So this minus charge shows that it has a lone pair on this carbon atom. So it shows that it is electron rich. This carbon, due to the presence of this lone pair, becomes electron rich, and nitrogen, due to the donation of this lone pair, becomes electron deficient. Then this minus charge or lone pair carbon atom to its nearing carbon atom, and it forms double bond between two carbon atoms, that is 3 and 4. Likewise, this minus charge travels or delocalizes from one position to its nearing position, and it shows different resonating structures. Then pyrrole molecule has the following molecular dimensions. Molecular dimensions of pyrrole has different bond angles and different bond lengths. So these are the different bond angles for pyrrole, and these are the bond lengths in Armstrong. Now we are going to see the basicity of pyrrole. Pyrrole is extremely a weak base because the lone pair of electron on the nitrogen atom is involved in the cyclic delocalization and is therefore less available for protonation. Moreover, pyrrole is a weaker base than pyridine and even than aniline. Okay, so pyrrole is a weaker base from than pyridine and aniline, in which lone pair on the nitrogen atom is involved in the resonance and not essentially contributes to the aromatic sextet. The protonation of pyrrole at nitrogen or carbon 2 or carbon 3 of the ring reduces its basicity and destroys its aromaticity. However, C and N alkyl substituents enhance the basicity of pyrrole. So to enhance, or whenever you have to enhance the basicity of pyrrole, you have to substitute carbon or nitrogen with alkyl group. But the electron withdrawing substituents on the ring make pyrrole as a weaker base. Okay, so withdrawing group, presence of withdrawing group reduces the basicity and it becomes weaker base. So these are the protonation reactions which are reversible in nature. The protonation at nitrogen, at first position, addition of hydrogen, it gives a structure which is a reversible reaction. So in this reaction, it is an addition or protonation reaction at carbon second position. Then here, protonation reaction at third position. Okay, so these all are reversible reaction. It is addition of hydrogen and removal of hydrogen. That is protonation reactions. Then the protonation of pyrrole at nitrogen is most rapid than that at C2 and results in thermodynamically more stable 2H pyrrolium cation. So the 2H pyrrolium cation which is formed is thermodynamically more stable, and 1H pyrrolium cation. So 2H pyrrolium cation which is formed is more stable than 1H pyrrolium cation, although carbon 3 is protonated but to a lesser extent. Moreover, the pK, that is minus 3.80 of its conjugated acid, corresponds to the protonation preferentially at carbon 2 rather than at nitrogen atom. Okay. Okay, so protonation at second position is very favorable and very more stable also. Then proton exchange. The hydrogen atom attached to the pyrrolyl nitrogen undergoes very rapid exchange in either acidic, basic or neutral media. Okay, so in any media that is acidic, basic or neutral, it undergoes rapid exchange. That is rapid proton exchange. But the exchange of C2H hydrogen attachment to ring carbon does not occur at an appreciable rate. The acid catalyzed hydrogen to deuterium exchange at the pH at the position 1 is 100 times greater than that of carbon 2 and carbon 3. Okay, so hydrogen to deuterium exchange at position 1 has faster rate, that is 100 times greater than position 2 and position 3. The rapid hydrogen to deuterium exchange at position 1 is attributed to the kinetically favored reaction due to very low activation energy for the NH bond breaking and bond forming in comparison to the activation energy for CH bond. Okay, so for NH bond it requires low activation energy and for CH it requires high activation energy. That's why there is a difference in the rate, that it is 100 times greater than that at 2 and 3rd position. The relative rate of alpha is to beta, that is hydrogen to deuterium exchange, is generally between 1.0 and 2.0 for pyrrole and 1 alkyl pyrroles. In 2 alkyl pyrroles, hydrogen to deuterium exchange is kinetically favored at position 3, while the exchange rate is highest at position 2 for 3 alkyl pyrrole. So in presence of D2O, okay, instead of H2O, here it is D2O. So in acidic or basic or neutral media, there is an exchange of hydrogen with deuterium. Okay. Similarly here, in presence of DCl, instead of HCl, here they are taken DCl. So there is a replacement of hydrogen with deuterium in final structure. Thank you.